Okay, so in this video we want to look at two things. We want to look first of all at working with formulas, so rearranging formulas and literal equations, which are essentially formulas, equations where we don't have numbers, we have variables instead. And then we also want to have a look at solving some worded problems, so that is setting up an equation in order to help us to solve a worded problem. Alright, so let's have a look at the formulas first of all. So first of all, the subject of a formula is the variable on its own, and it's usually written on the left-hand side. For example, in this formula here, a equals pi r squared, a is the subject of that formula. We have a in terms of r, okay? A, we're being told what a is equal to. A is the subject of the formula, okay? In the formula a equals L times W, we would say that a is written in terms of L and W. In the formula, L equals, and therefore A is the subject of this formula also. In the formula, L equals A over W, which is simply a rearrangement of the same formula above. This time we have L as the subject, and we would say that L is written in terms of A and W. It's really important to start to understand that language. That's something that's commonly asked for down the track, express the volume in terms of X. And I find a number of students get confused and they try to get their equation as X equals, but it's asking you for volume, so V equals, in terms of X. Your expression for volume will involve X, okay? A formula can be transposed or rearranged to make another variable the subject. Okay, so let's have a look at these examples. So here we have a formula, v squared equals u squared plus 2ax, and we want to transpose this formula to make a the subject in part A. So again, this is about order of operations and how are expressions built, okay? If you understand what you're doing when you're solving equations where there's numbers, it should be a very simple process to transfer across to rearranging formulas. If you don't really think about what you're doing when you're solving equations and you just see it as a process of shuffling things around, you will find working with formulas really difficult because you fundamentally don't understand what you're doing, okay? So it's really important that when you learn the simple things, you focus on developing understanding about what it is that you're doing so that when that's then extended to something else, it still makes sense. And that's the challenge that I want you to sort of start to grapple with in Year 10. If you've spent a lot of Year 7 and 8 and 9 just sort of shuffling things around and using rules and subbing into rules and not really thinking about what you're doing, your mathematics career is going to very quickly get quite difficult here, okay, because you're going to struggle to extend your understanding of things you've already learned into new territory. So here we want to focus on what is happening to A, because A is what we're trying to make the subject. We're trying to get A on its own, so what is happening to A in this expression on the right-hand side, and therefore how do we undo those things? Okay, so A is being multiplied, now it's written in the middle, but that's the same as 2xa. It's being multiplied by 2x, okay? So this formula starts with A gets multiplied by 2x, and then we're adding on u squared. That's positive u squared and positive 2a. So we're adding on u squared. People get confused about the squares. Oh, opposite of squared, square rooting. I need to square root things. But the a isn't being squared. So there's no squared that needs to be undone. Okay? We're adding on u squared. So the first thing we're going to do here to get a on its own is to subtract u squared from both sides of the equation. That's undoing that step. Okay? So if we subtract u squared, I'm just going to write out the original formula. V squared equals u squared minus 2ax. If I subtract u squared, sorry, it's not minus, it's plus 2a. If I subtract u squared, I'm going to get v squared minus u squared equals 2ax. And then I can divide by 2x, which would be undoing that step, in order to get a on its own. So dividing both sides by 2x, and I want to make a the subject, so I'm going to write it on the left-hand side. So a equals v squared minus u squared divided by 2x. Two simple steps required to get a on its own. If we want to take the same formula and make u the subject, so v squared equals u squared plus 2ax, okay, so this time here's the u, here we're making a the subject, okay. So the first thing happening to u is that it's getting squared, so that's the last thing we want to undo. Then we're adding on 2ax. So that's the first thing we want to undo. We want to subtract 2ax from both sides. So we get v squared minus 2ax equals u squared. Alright, we've nearly got u on its own, it's just being squared. So the opposite of squaring is to take the square root. And when we take a square root, we need to be careful about the fact that it could be positive or negative. Okay, so for example, if we have this simpler equation, x squared equals 9, x equals 3 is only one of two possible solutions. Okay, x could actually be positive or negative 3, because positive 3 squared is 9, but negative 3 squared is also 9. So when you take a square root, plus or minus the square root of 9 means we get plus or minus 3. You must always consider that it could be positive or negative. So if there's nothing in the information that says this thing must be a positive thing or must be negative, for example, nothing here says u is a positive, that u is bigger than 0, then we have to write the plus minus. So u is going to be positive or negative square root of v squared minus 2ax. Now again, the square root and the squared underneath there, they don't cancel out because you've got to do the subtraction before you do the square root. There's brackets implied here in that big square root, and so you can't just override them and square root this bit first, okay, before you do the subtraction. Alright, question 2, rearrange each of the following to make the variable in the brackets the subject. So k equals 3l plus 4m, and we want to make m the subject. So again, identifying what is happening to m. The first thing happening to m is that it gets multiplied by 4, and then we add on 3l. So the first thing we want to undo is the opposite of adding on 3l, which is to subtract 3l. So we're going to get k minus 3l equals 4m, and then we're going to divide both sides by 4, which means that m is going to be equal to k minus 3l divided by 4. Okay, part B. Now before you can sort of think through this kind of process for part B, if the unknown that you're trying to make the subject is on the denominator of a fraction, the first thing you've got to do is get it out of the denominator, then you can focus on getting it on its own. Okay, so in this instance, this is easy enough. If we multiply both sides of the equation by 4r squared, we're going to get 4r squared t on the left, and multiplying the right hand side by 4r squared simply cancels out the denominator, and we'll just be left with a. Now we can focus on what's happening to r and how do we get it on its own. So the first thing happening to r there is it gets squared, and then it's being multiplied by both 4 and t, so it's being multiplied by 4t. So we're going to divide by 4t first, so r squared equals a divided by 4t, and then we're going to take the square root. So r is a positive or negative square root of a over 4t. Oh, sorry, not 4 pi, 4t. Okay, part C, we want to get h on its own. So here is h in the equation here. The first thing that's happening to h is that we're adding k, then it gets divided by g, then it gets square rooted, and then it's multiplied by 2 pi. So lots of steps there, and we're going to run out of room here, but that's okay, we'll work around it. The first thing we want to undo is the multiply by 2 pi, so we're going to divide by 2 pi. So we're going to have p over 2 pi equals the square root of h plus k on g. Careful how you write the square root in that instance. Make sure it's square rooting the whole fraction, that it doesn't become a bit ambiguous about, oh, is it just the numerator or denominator, or the whole thing under the square root. Okay, so we've done the opposite of multiplying by 2 pi, which is to divide both sides by 2 pi. Then we want to do the opposite of square rooting, which is to square both sides. So we're going to get p on 2 pi all squared. Now you can write that as p squared on 4 pi squared if you want, or you can just leave it as the whole thing squared. We've got h plus k over g. Okay. Now we're going to multiply both sides by g. I might write one more line up here. So we're going to get g times p over 2 pi squared equals h plus k. And then the last thing we want to do is subtract h from, what are we making the subject? H, so subtract k from both sides. So h is going to be equal to g times p squared on 2 pi, take away k. Oops, sorry, it's p on 2 pi all squared, take away k. We can leave our answer as that. As I said, you could expand out that fraction, so that's p squared on 4 pi squared if you prefer. You could then combine those fractions together there, so that becomes gp squared over 4 pi squared minus k, okay? But really either this one or this one. If you've expanded this out, then I would definitely put the fraction together with the g. So either that row there, that line there, or that line there, both acceptable answers to the question. Okay, and part D here, we're making t the subject. So the challenge here is that t is in two places in the equation. So the first thing we need to focus on is getting those t terms together. Okay, let me just detour for a minute and imagine that this was a numerical equation. So let's imagine that this was, 8t equals 2s, that doesn't matter what that is, just be a number, we'll just leave it as 2s maybe, minus, I'll just make it something, I'll make it 6, equals 3t. Sorry, not equals 3t, minus 3t. Okay, so imagine it's this equation. We need to be able to see that they are the same. They're the same in shape, and so if we can solve this number equation, we should also be able to solve this formula. So we would add 3t to both sides, and we would normally collect the like terms together in our head, but I'm going to write it as a separate step just to help us see what's happening. So we get 8t plus 3t on the left equals 6 on the right. And then when they're numbers, we can collect like terms easily, because we know that 8 lots of t plus 3 lots of t gives us 11 lots of t, and we'd just write 11t. But one of the reasons the only terms that we can add together are like terms is because we're adding them, what we're doing is we can only add them together because they have a common factor of t. So actually we're thinking about that this is 8 plus 3 lots of t. T is a common factor. Now whether you write that at the front of the bracket or at the back, it doesn't matter, it's the same thing. T is a common factor, and that's why it is 11t. Okay, it's why 8t plus 3t is 11t, because it is t lots of 8 plus 3. And so then t is 6 on 11. So we want to follow these same processes here. Let's get the t terms on the one side, so I'm going to add vt to both sides. So ut plus vt equals 2s. And then we need to collect these like terms together, and the way we're going to do that is to factorise like we did over here. T is a common factor. If we take that out, we get t times u plus v equals 2s. And in having done that, we've gone from having two t's in the equation to just having t in this one place. So now we just want to get t on its own. T is currently being multiplied by that bracket, and so to get t on its own, we're going to divide by that bracket. That's a really important technique that happens frequently when we're rearranging formulas and solving literal equations. Okay, if you need to collect like terms, you want to factor out the thing that you're trying to make the subject. Okay, you can rearrange formulas with your CAS, so let's try and get our CAS to do D, and again it's just about using solve. And this is why we need to tell it put comma whatever we want to solve for, because if we've got more than one letter in our equation, we need to tell it what we want it to solve for. So actually I might just go back and demonstrate example 1 first, and then I'll do that last one again. So menu 3.1 for solve. You want to type in your formula, so I'm going to type in this formula. And we do need to be a bit careful when we're entering in formulas. So I'm just going to type it in, b squared equals u squared plus 2ax. Now, if you type 2ax, and then we want to make a the subject, so comma a, and press enter, I'm going to have trouble here. My CAS is not doing what I'd expect, the answer's not right, it's doing something strange. Now what I want you to notice here is when I typed in the equation, I just typed 2ax and I didn't put any multiplication signs in. I just typed 2ax like it's written on the paper, 2ax. When I pressed enter, my CAS, I can't write in here, my CAS has inserted, let's see if I can just highlight what I mean. Oops, sorry. My CAS has just inserted a multiplication sign in there. Okay, I didn't type that, it did it. It knows that when I write 2a, 2 letter, that I mean 2 times a, 2 times whatever letter. Okay. However, what you should notice is it hasn't inserted a multiplication sign between the a and the x. It hasn't assumed that I mean a times x. And that's because you can use words as variables in your CAS. So my CAS isn't understanding that as 2 times a times x. My CAS is understanding that as 2 times ax, where ax is an unknown in its own right. It's not identifying those as separate letters. And that's why when I've asked it to solve that equation for A, my CAS actually doesn't recognise that there is an A in that formula, because it sees V, which is being squared, U, which is being squared, and X, which is being multiplied by 2. And I haven't asked to solve for any of those things. So we need to be really careful about this. So I'm going to use that answer. I'm going to scroll back up. I'm going to press enter to copy that down. And I'm going to type what I mean, which is 2 times A times X. So anytime you have two non-numeric characters, two letters next to each other, sometimes this problem also arises when you have a letter and then a bracket and then a letter. For example, X times bracket X plus 3, you would need to put the times in. So be explicit about it, and now it should be able to see the A and it should be able to rearrange this formula. Now, the CAS often does loves to factor out negatives when it's not really necessary. But we just need to better recognise that our answer is the same. So we've got V squared minus U squared. They've taken out a negative and written U squared minus V squared. If we were to expand out their answer, okay, so put this negative, which is -1 times all of that, back into the bracket, we would get negative U squared and positive V squared, which is V squared minus U squared. So it's the same thing. Now in part B of example 1, we rearrange the same formula to make U the subject. So if I scroll up, press enter to copy down this line, and instead of solving for A, change that to solving for U. We should get our formula. Now it gets a bit ugly with the square roots, but if you have a look at, here's the first bit that I'm interested in. U equals the negative square root of V squared minus 2AX. This bit here is just about saying that it's only going to be true if certain things are positive, so we don't really need to worry too much about that right now. And here's the other part of my answer, U is equal to positive square root of V squared minus 2AX. So it's the same answer we got. Let's have a quick look at D. Let's just enter that in. So menu 3.1, type in your equation. So U times T, right? You have to explicitly put in the multiplication, equals 2 times S. Now, I don't need to write 2 times S, I'm just going to write 2S. You can, it's fine. I'm just going to write 2S though and show you that the CAS understands that. Minus V times T. And comma, what do we want to solve for here? T. If I press enter, so you'll see there's no multiplication sign written between the 2 and the S, but when I press enter, my CAS goes, oh, 2S means 2 times S, and it adds it in for me. So have a watch. And there we go. The multiplication's added in there, and it's rearranged to make T the subject, and it's got the same answer that we did. T equals 2S over U plus V. Okay, let's have a look at using equations to solve worded problems. Now, I really want you to understand that this is such an important technique, okay, such an important skill for moving forward in maths. Being able to translate from a problem in words to a problem in algebra is one of the hardest things to develop, and something that we really need to practice because it's super, super important going forward into maths methods. Okay, so the point is here is that when you're solving worded problems in Year 9 and 10, the goal isn't, what I'm looking to assess isn't what's the answer to the problem. I don't really care what the answer to the problem is. Okay, fine, that's the easy bit at the end. What I'm interested in is your ability to formulate the equation. That's really what I'm looking at testing and assessing here. So I am not interested in a trial and error method whereby you can come up with the answer. That's not, okay, that's exploring numbers and being able to do good number work, and that's going to be, you know, potentially excellent if you're going to go on to do further maths. But if you're going on to do an algebraic course, what we're trying to develop here is your algebra skills, and the skill is the translation from the worded problem into the algebra problem. Okay, so I want you to focus on that. I don't care if you can get to the answer by playing around with the numbers. I'm interested in the formulation of the equation. That's the hard bit. That's what we're testing. That's what we're learning. Okay, so don't cut corners here. All right, so let's work our way through a series of examples. So I want you to think about it as a 4-step process. One, you want to clearly define a pronumeral. And when I say clearly define, I mean be precise in your definition. For example, x equals apples is not a clear definition. Apples isn't a numeric quantity. What about the apples is x equal to? Is x equal to the number of apples? X equal to the weight of the apples? X equal to the cost of an apple? Whatever it is about the apple. Is x equal to the diameter of the apple? Whatever. Okay, what numerical quantity about the apple does x equals? Because that will help you when you are reading your algebraic sentence to see if it makes sense, okay? The second thing is to construct the equation. That's written very flippantly there at step 2. That's the hard bit. Step 3 is to solve the equation. That's the easy bit. Once you've built the equation, solving it's easy. Step 4 is to then make sure that you've actually answered the question. So perhaps when you, in the problem, when you formulated the equation, it was easier to let x be the number of bananas, but the question actually asks you for the number of apples. So when you've solved the equation, you haven't actually found the number of apples, you found the number of bananas, and you then need to make sure that you calculate and answer the actual, what the question's actually asking you. Okay, let's work through the examples. 3 consecutive integers add to 72. Find the largest of the 3 integers. Now this is probably pretty easily done by a bit of trial and error, but again, it's about the formulation. So consecutive integers are integers that are in a row. Okay, integers being whole numbers, 3 whole numbers in a row. For example, 5, 6, 7 are 3 consecutive integers. 2, 3, 4 are 3 consecutive integers. 105, 106, 107 are 3 consecutive integers. Okay, so we want to think about how we can represent those algebraically. Okay, so the question asks us to find the largest of the 3 integers. So if we were to, don't write yet, let's just listen for a minute. If we were to let x equal the largest integer, then if we wanted the second largest integer and then the smallest integer, okay, well if x is the biggest one, then x minus 1 is the next one down and x minus 2 is the next one down. Now they're going to work. We can build it, then build the equation with those 3 variables. However, to me it's actually easier to let x be the middle integer. And as I said, there's nothing wrong with the first option. I just like to set things up in a way that generates the simplest possible equation. So if I let x be the middle integer, that's going to mean that x plus 1 is the largest integer and x minus 1 is the smallest integer. The other thing I wanted to say here is when you're dealing with worded problems, students, in my experience, students struggle with them in part because they sit there and they stare at it and then they put their hand up and say to me, I don't know how to do this. And they haven't actually done anything. Please don't assume that you should be able to read the question and immediately write down an equation. That's not how it works, okay? You need to build up the equation. Okay, what am I going to let the unknown quantity be? How can I describe the other quantities in the problem in terms of that unknown? And then how can I compile together all those unknowns into an equation? Okay, it's about building it up. Don't expect that you can just write it down straight away. Okay, so these are my 3 integers, x, x plus 1, and x minus 1. They're 3 consecutive integers where x is the middle integer, and I know that they add to 72. So x plus 1 plus x minus 1 is equal to 72. 72, sorry. Okay, so we've defined a variable. We've then described the other quantities in terms of that same variable, and then we've been able to combine them together into an equation, which we can now solve. Alright, on the left-hand side, we've got x plus x plus x, so 3x minus 1 and plus 1, they cancel out, equals 72. And then x is going to be 72 divided by 3. 60 divided by 3 is 20, and 12 divided by 3 is 4, so this is 24. And then I want to answer the question because I'm asked to find the largest of the 3 integers. We've found the middle of the 3 integers, and so therefore the largest integer, if the middle one is 24, the largest one is 25. Answer the question. Okay, question 2. 65 lollies are divided amongst three friends so that Alan has twice as many as Brendan and Chris has one more than Brendan. How many lollies does Chris get? Okay, again, what do we want to let the unknown be? Now I could let, A be the number of lollies that Alan has, or B be the number of lollies that Brendan has, or C be the number of lollies that Chris has. I don't want to introduce 3 different variables. If I introduce 3 variables, I need 3 equations. I want to try and introduce one variable and then express the other quantities in terms of that variable. So for me, the easiest place to introduce the variable is to let Brendan's lollies be the variable, because we're told about how many lollies Alan has compared to Brendan, and we're also told about how many lollies Chris has compared to Brendan. So it's going to be easiest to to construct my other variables if I let the unknown quantity be the number of lollies that Brendan has. Okay. Now I don't like lowercase b in algebra because it can often look a bit like a 6. So I'm going to let, you could use a different letter, I'm going to use b, but I'm going to use uppercase b. I'm going to let b equal the number of lollies Brendan has. Okay, again, b doesn't just equal Brendan. Brendan's not a quantity, Brendan's a person. Okay, so it's the number of lollies he has. Okay, so that means that Alan has twice as many as Brendan. So Alan has 2b lollies. And Chris has, what does Chris have? Chris has 1 more than Brendan, b plus 1 lollies. So now we've got our 3 quantities, Brendan's lollies, Alan's lollies, Chris's lollies, and we know in total there is 65 lollies, so we know that b plus 2b plus b plus 1, doesn't matter what order I put them in, but that's okay, equals 65. Then we can solve that equation. B plus 2b plus b is 4 lots of b plus 1 equals 65. So 4b equals 64. Dividing by 4, 40 divided by 4 is 10, and then 24 divided by 4 is 6, so it's 16. So that is the number of lollies that Brendan has. What does the question actually ask for? It asks how many lollies does Chris get. Chris gets b plus 1, so therefore Chris gets 17 lollies. Okay, example 3. Jackson has a square garden bed in his yard. He decides to enlarge the garden bed to make it 1 metre wider and 2 metres longer than it is currently. If the area of the new garden bed will be 14 square metres larger than the original garden bed, find the dimensions of this new garden bed. Okay, so let's have the original garden bed. That was a square. Okay, so let's call that x by x. And then he decides to make it 1 metre wider and 2 metres longer. Okay, so that's 1 and that's 2. Okay. If the area of the new garden bed will be 14 square metres larger than the area, than the area of the original garden bed, find the dimensions of the new garden bed. Okay, so the new area is the original area plus 14. So the new area, the dimensions of the new garden are x plus 1 times x plus 2, and x plus 2. So the new area is going to be x plus 1 times x plus 2. The original area, which is this bit, is x times x, so x squared plus 14. So there's my equation. Let's expand out the brackets on the left-hand side. X times x is x squared, x times 2 is 2x, but I'm not going to write that down because I know it's going to collect together with the next term. So I've got 2x plus 1 times x, which is 1x, so 2x plus 1x is 3x, and then 1 times 2 is 2, equals x squared plus 14. Let's subtract x squared from both sides. We get 3x plus 2 equals 14. Let's take away 2 from both sides, so 3x equals 12, and x equals 4. Okay, so then let's answer the question. Find the dimensions of the new garden bed. Okay, so therefore, new garden, the original garden was 4 metres by 4 metres. The new garden is 4 plus 1, so 5 metres by 4 plus 2, which is 6 metres. And you can check that. The original garden was 4 by 4, which is 16 square metres. The new garden is 5 by 6, which is 30 square metres. 30 is 14 bigger than 16. Okay, question 4. Fred is 25 years older than Bill, and in 5 years he'll be twice as old as Bill. Find their present ages. Okay, this is a really common kind of example, and I find that students make mistakes with these quite frequently because they end up trying to construct an equation where they compare Bill's current age to Fred's previous age, and that's not what the information says. Okay, so you need to be consistent about your variables. There are there are 4 quantities here. Fred's current age and Bill's current age. Fred's age in 5 years and Bill's age in 5 years. So you need to organise and get those variables straight first and then work out how to build your equation. Okay, so I'm going to have Fred and Bill and I'm going to have now, and what's the other time period? In 5 years. Okay. We want to know both Bill and Fred's present ages. I only want to introduce one unknown. I'm going to either call that X or I'm going to call that X. Now, it says Fred is 25 years older than Bill. So it doesn't matter. If we let X be Fred's current age, then Bill would be X minus 25. Or if we let Bill be Bill's current age be X, then Fred would be X plus 25. So they're both there's no preference over those two things. They're both as simple to work with as the other. Okay, then I'm going to pause and not read any more about the question because I know that the second column is 5 years later than the first column. So we're going to add 5 years onto each of their current ages. If Bill is currently X years old, in 5 years he'll be X plus 5. If Fred is currently X plus 25, in 5 years he'll be X plus 30. Okay, now the information from the question is all about what's happening in 5 years. So we want to use the variables in the yellow column that I've just highlighted. In 5 years, so the he there refers to Fred. If you read the full sentence, Fred is 25 years older than Bill, and in 5 years Fred, will be twice as old as Bill. So in 5 years, Fred will be twice as old as Bill. Okay, so what we know is that Fred's age in 5 years is equal to 2 times Bill's age in 5 years. So we shouldn't be using any of the variables in the now column, okay, because the information is all about what's happening in 5 years. In 5 years, so using the right-hand column, Fred will be twice as old as Bill, okay? So Fred's age in 5 years is X plus 30, and that is equal to 2 times Bill's age at that same time, which is X plus 5. Again, the construction of the equation is the hard bit, the solving is the simple bit. Let's expand out the right-hand side. 2 lots of X plus 5 is 2X plus 10. Subtracting X from both sides, so 30 equals X plus 10. Subtracting 10 from both sides, 20 equals X. So then answering the question, we want both of their present ages. X is Bill's present age, so therefore Bill is 20 years old, and Fred is 25 years older than Bill, so Fred is 20 plus 25, 20 plus 25, so 45 years old. And again, you should be able to check it. Okay, Bill is currently 25 years old. Fred is currently 25 years older than Bill. Yes, that's correct. In 5 years, we know Bill would be 25 and Fred would be 50, and so yes, it makes sense that Fred is now twice as old as Bill. Okay, question 5. Mr. Jessup is training for an Ironman competition. On Saturday, he trained for 6.25 hours, completing a bike ride followed by a run. He cycled at an average speed of 30 kilometres per hour and ran at an average speed of 16 kilometres per hour. If he travelled a total distance of 170 kilometres, find the time that he spent on the bike. Okay, so in these kind of problems, again, these are quite common. These distance, speed, times and different aspects to a journey or 2 parts or travelling from A to B and then from B back to A or whatever it might be. These are quite common problems, and again, the challenge here is that there are a lot of unknown quantities. Some of them are known, but there are a lot of quantities, a lot of variables to be dealing with. Okay, so we have the bike ride and the run, and for each of those two things we've got information about distance, speed and time, and we also have information about total distance, and we also have information about total time. So we actually have 8 quantities that we're working with here. So let's focus on organising that information first. Okay, so we're going to have distance and time and speed, and we need to be careful about units here, that we're consistent about units. The speeds should guide your units, so the speeds are in kilometres per hour, which means my distances are going to be in kilometres and my times are going to be in hours. Okay. Alright, so we've got the bike ride and the run, and then we might also have information about totals. Total speed is a meaningless quantity, won't be anything in there, but the other 8 boxes we want to try and think about filling in. So start by filling in what we know, then we'll work out where we should put x, and then we'll try and describe the other quantities in terms of x. So on Saturday, he trained for 6.25 hours. Okay, so time in hours is 6.25, or 6 1/4, or 6 is 24 quarters, so or 25 quarters. There's nothing wrong with 6.25, just sometimes it might be easier to work with the fraction. You don't need to worry about that. When you build your equation, maybe you think about changing it then. He completed a bike ride followed by a run. He cycled at an average speed of 30 kilometres per hour. So the bike ride speed was 30, and he ran at an average speed of 16 kilometres per hour, so the running speed was 16. If he travelled a total distance of 170 kilometres, so total distance is 170, find the time that he spent on the bike. Okay, so we want to know this time, okay? We've got to, now that might not be the best quantity to let be the unknown, but let's see how we go. But let's start with that. So the advantage here is that we also have a connection between distance, speed, and time. Okay, so we know that speed is distance divided by time. So we can construct this triangle. If you haven't seen this before, I always start with the fact that speed equals distance over time, okay, to build the triangle. And the easiest way I know that is because kilometres divided by hours is the units, distances divided by time is the units. When you build this triangle, you then, if you cover up the thing that you're trying to find, so if I cover up the s, I'm left with d over t. Speed is distance over time. Okay. If I cover up the t, I'm left with d over s. Time is distance over speed. If I cover up the d, I'm left with st, s times t. Distance is speed times time. Okay, so in this column here, I can now fill in the distance row because I know that distance is speed times time. So if the cycling speed is 30 and the cycling time is t, then the cycling distance is 30t, 30 times t. I can also fill out this time because I have the total time. So if the cycling time was t hours and the total time was 6.25 hours, then the running time was 6.25 take away t. And again, the running distance is the running speed multiplied by the running time. Okay. Again, we can write that 6.25 as a fraction if we prefer. And now the top row is going to give me the equation. The cycling distance plus the running distance has to total together to give 170. You're not going to get the equation from here because you used the total time to come up with the running time. So simply adding up the cycling time and the running time to equal 6.25 is only going to tell you that 0 equals 0, and it'll be true but not useful. Okay, so because you've already used it, it's no longer useful information. So the total distance is what's going to enable us to build the equation. Okay, so we know that 30t plus 16 times, I am going to write that as 25 on 4, take away t. If you're happy working with the decimals, that's no problem at all, equals 170. Okay, so I want to expand out the bracket, so 30t plus, now if I'm doing 16 times 25 on 4, remember that's 16 over 1 times 25 over 4, the 16 and the 4 are going to cancel down, so I've now just got 4 times 25, so that's going to be 100. Okay. You might have been comfortable doing the 16 times 6.25 instead. 16 times 6.25 to think about, well, 16 times 6, 10 6s is 60, 6 6s is 36, and then 16 times 0.25, or 4 times 0.25 is 1, 16 times 0.25 is 4, and adding it up that way. But personally, I'm happier working with fractions. It's more about whole numbers. So what did we decide that was? It's 100. And then take away 16 times t, take away 16t equals 170. 30t minus 16t is 14t, plus 100 equals 170. Take away 100, 14t equals 70t. t equals 70 on 14. Now you might know what that is off the top of your head, but if you don't, that's fine. Just break it down. 7 goes into both of those, so that's 10 on 2, which is 5. So therefore 70 divided by 14 must be 5. If you knew that straight away, fine. If you didn't, you can still get there just with one extra step. Okay, so t equals 5. Let's be clear about what the question asks for. Find the time that he spent on the bike, so that is what t is, and it's in hours, so therefore he spent 5 hours on the bike. So he must have spent the remaining 1.25 hours running. Okay, so some practice today from exercise 1D.